We continue the fourth lecture on network science with an example on the eigenvector centrality. So that's a natural continuation of the previous video. So on the figure here in the middle, you can see a simple example of a graph. And on the left-hand side and on the right-hand side, you can see the corresponding adjacency matrix. Now, the graph which we have is undirected, and we can very easily calculate the degree centrality scores, which are listed here. So this 0.2 corresponds to node 1, node 2 is 0.4, node 3 is 0.8, node 4 0.4, node 5 0.6, and node 6 is 0.4. Now you are wondering how on earth we have non-integer numbers here. Well, in many cases what happens is that the centrality scores or the centrality measures are normalized. So it means that um, mm, the degree, for example, for node 1 is 0.2, which means that it's what is, so you can see that the real degree here is actually 1. So instead of having 1 here, what we have as 0.2 is 1 over 6 minus 1. So in general, we have, so down here you have the number of nodes, which is n, and we always divide by n minus 1. So node 2 has a degree equal to 2, and then in this normalized fashion is actually 2 over 5. And node 3 is having 3 edges, and hence the corresponding normalized degree is 0.4, 0.8, and so on and so forth. So I was basically indicating here the degree centrality is just for the comparison. Okay, now you can see that that according to the degree centrality, the most important node in this network is node 3. And indeed, that is somewhat located in the middle, and it's connected to 4 other nodes. And there is no other node in the network which is connected to that many nodes. So taking the adjacency matrix now and using so-called power iteration, we can calculate the largest eigenvalue of A. So the power iteration is the iteration which we discussed in the first video. So that's just an iterative method which in this case actually is guaranteed to converge. Now the reason for that is related to numerical mathematics, and in particular to the matrix itself, so the adjacency matrix, some properties of the adjacency matrix, whatever the graph is. And so if we calculate the largest eigenvalue, then what we get is indicated here as kappa 1, and it's 2.771 something. And the corresponding eigenvector to that maximal eigenvalue is listed here or indicated here. And so similarly, like before, this is node 1, node 2, node 3, 4, 5, 6. And now we can see that still the largest, so the most important node, even in this small graph, is still node 3, which is not really a surprise. What is interesting, on the other hand, is that node 4 and node 6, they still have equal centrality values, similarly to the case of the degree centrality. So you can see, and that's still not really surprising, because both of them, so you can see on the graph that these two nodes are, you know, some kind of reflections of each other. So the graph is pretty symmetric in this sense, I mean, some kind of geometrical sense. But okay, so now let's see that also the node 5 is also the second most important node, and that's still in line with the degree centrality. And now what is interesting and what makes a big difference here is the case of node 2. And you can see again back in the for the degree centrality that node 2 so node 2 is actually equally important to node 4 and node 6 for the degree centrality. And now here the importance is much lower than for node 4 and node 6. And so now we can maybe have a look on the figure again and consider and try to understand what's happening here. So node 2 is connected to node 3, and node 3 is the most important node. Hence, node 2 is supposed to be an important one. But compared to node 4 and node 6, they are also connected to node 3, as you can see, but they are also connected to node 5, which is not the case for node 2. So since node 4 and 6, they are connected to node 5, and node 5 is connected to node 3, which is the most important node, and this makes the second most important node of node 5, not alone, of course. It's also, the fact is also counted or taken into account that it is connected to node 6 and 4. So anyway, by the fact that 4 and 6, both of them are connected to 5, it makes them more important. Okay, so this is a small, but I think it's a very nice example to show the somewhat interesting difference between the degree centrality and the eigenvector centrality. And so now because the size is not that big, now it's kind of easy to see, and maybe without exactly writing down the numbers here, maybe we can even detect or guess the ranking of the nodes with respect to eigenvector centrality for this particularly smallish graph. All right. So let's see what's the case for eigenvector centrality in directed networks. So again, for directed networks, it is a very nice example to consider the World Wide Web. And the question comes immediately that if we have a web page, P, which links to other 1000 pages, then the question is, does this make page P important? So, well, it depends, of course, because then web page P, it can really connect or link to very important nodes, but in in a well, if it's if there is a connection back to page P, then it's a different picture, of course. But Maybe nowadays we can also think about the Twitter example, as that also makes so following follows link on Twitter, that also makes a directed network as a case, or as a example or model. And if I'm following 1000 important people, importance now means some kind of political importance, or popular importance, or artistic importance, then this simple fact doesn't make me important. But there is even a more fundamental problem here, which is well, it's demonstrated here on node. So on this small graph, which is just a part of a much bigger graph. Okay, and so now you can see that. So now we should consider the situation for node A and node B. Now, node A, as simply by the fact that it has only outgoing edges, then the eigenvector centrality score for that node is basically 0 in case of if we consider the network as directed network. And the case for node B is actually interesting, because it has two outgoing edges, this one and this one. And there is one incoming edge from node A. Now, node A has 0 eigenvector centrality, and hence, because there is no incoming edge, okay? And this gets propagated to node B as well, um, and that is a problem, okay? So the slide says that the score of A is 0 because no vertex is pointing to it. Okay, that's cool, that's fine. But the score of B is also 0 because there is only one node A which links to it, and the eigenvector centrality of A is 0. So that is not cool. So that is that shouldn't be the case. Okay, now nevertheless, so there is of course a remedy for this, but before discussing that procedure, how we can fix this problem, we might want to mention some notes here, which states that for directed networks, vertices which have non-zero eigenvector centrality scores are usually members of strongly connected components having at least two vertices, and they are actually out component of this kind of strongly connected components. So this is an OR. Okay, this is just I mean this statement goes further away, of course, which we don't really want to go on. So I just wanted to mention that nicely the some of the characterizations of zero, non-zero eigenvector centrality nodes for directed networks are given. On the other hand, if we have an acyclic network and the directed one, so DAG, they, of course, they don't contain strongly connected components, because you remember, right, that the strongly connected component is a set of nodes which are connected in a directed way on a directed path, actually on both directions. So from node A to node B there exists a directed path, and from node B backwards there exists again a directed path to node A. So this acyclic network, the DAGs, they cannot, by definition, they cannot contain strongly connected components, and hence the eigenvector centrality does not make sense on this kind of network. For example, on citation networks, if the citation network is a dog, and it is, uh, it's not really a useful it's not really a useful a centrality measure to be calculated on that kind of graphs in a directed sense. Okay, now let's see that remedy which I mentioned earlier. So, well, that is called cut centrality, and it's a quite simple remedy for the problem, which is described in the previous slide. So that I mean, motivated by this small figure here, that that A has zero value, and then B also has zero value. So let's see what was proposed by Katz. He was actually proposing a very basic idea that we should give a small initial score for free to each and every node. Okay, so the previously the formula was that x sub I should be a multiplication of aij multiplied by j, and then xj, and then the summing should be going for all the j's. And so, or put it into a vector matrix format. This was the form. And so actually what Katz was proposing, that we should maybe give some initial score for free. That should be some beta value indicated here, and beta is larger than zero, strictly larger than zero. The choice of it is a detail which we are not discussing, and then maybe we would also like to multiply the matrix with another parameter alpha, which is maybe it could be 1. But again, I'm not willing to discuss the details. And if we have this kind of matrix vector write up, then we can rearrange it a bit and get the famous formula for the cut centrality, which you can see that it includes matrix inversion, which of course we never calculate the inverse of the AJSSE matrix, or some transformed version of the AJSSE matrix. So this is just a mathematical formula. Of course, the whole thing is again calculated with using iterations. So now, of course, the centrality value itself is never really considered as the value itself. So I mean, here previously we compared the degree centrality vector with the eigenvector centrality, and so I never mentioned that here for the degree centrality, node 3 has much bigger centrality value than in eigenvector centrality, because the number itself, it doesn't matter, or well, most of the cases it doesn't matter, unless we are really interested in like if this small graph was a friendship network, and we are really interested in the number of friends someone has. So I mean, if the scores in an absolute sense they don't count, then of course they count in a relative sense, and in a relative sense it's actually considered. So basically the centrality vector is considered as a ranking how to say this, ranking methodology. Okay, so and basically it turns out that beta can be chosen for being 1, and then the final formula for the cut centrality is given here. Okay, here the alpha needs to be chosen using some proper techniques, but I'm not really willing to go into the details. If you are interested in it, then please refer to the book of Newman. Okay, now continuing the discussion on this cut centrality, I mentioned that you can see it yourself that the formula involves inversion of the matrix, which we usually never calculate, but instead, as I mentioned, we should do again some kind of power iteration starting from a completely zero vector and do the iteration here, which maybe we would like to write in this way, that it should be k plus 1, and then here it's x k, okay, and k goes from 0, 1, and so on to infinity. And then again, due to the fact that the matrix of so A matrix A has some nice properties, which due to numerical mathematics, the convergence is guaranteed. So right, so here downstairs on the bottom of the page, there are some discussions about how many steps we need to take, how many iteration steps we need to take. Well, you can read that that it's not easy to find out, but still we should never really do the inversion of the matrix, which was indicated in the previous slide. Okay, now so this was the case for actually directed networks. It can also be given for undirected ones. But interestingly, if we have undirected networks, a node which has lots of neighbors, so the degree centrality of a node is large, then even in the case if its neighbors have low centrality scores, then the centrality score for a given node can be kind of large. Okay, and hence the question emerges if this cut centrality is the perfect centrality measure. And the answer is something like not really, because if we have a node, for example, which has somehow large cut centrality, and so what's happening here is that if a node has a large cut centrality measure, then obviously that also indicates that the neighbors of it can have large centrality value, cut centrality value. And so the last point here is it says that you are 1 in a million, with which what I'm referring to is that kind of simple fact which I mentioned like 5 minutes ago, that just basically the fact that I'm following someone on Twitter who has lots of followers, then this simple fact doesn't make me important, because I'm just one in a million. Okay, or if there is an important website, a news website, BBC website or something like that, and then there are other very small websites, I mean very, like not important websites, but they are all referring to the BBC website, then this simple fact doesn't make them important, because they are just one in a million again. So Before we move to the final version of the eigenvector related centralities, let me show you a small figure again, in which now we have 6 colorings for the same graph, and actually so far we have the so sorry, it's actually rotated the figure. Okay, so C is shown as the eigenvector centrality, then D is shown as the degree centrality, and F is shown as the cut centrality. And again, if we have a blue node, then it means low centrality value, and red node or red coloring means higher importance. And you can see that that for the different centrality values for the exactly same network, we get pretty much different rankings, even between C and F, which are somewhat related to each other, which is, I think it's quite interesting. Okay, now the last centrality measure among the eigenvector related centrality measures is the so-called PageRank, which is maybe the most well-known and celebrated formula since its invention, which was actually invented by or proposed by the founders of Google. And it was their basic algorithm or basic methodology to find out that what are the most important websites on the World Wide Web. And the idea is somehow a continuation of the cut centrality. So here again in the formula you can see a factor beta, which is meant to be a remedy for giving just a small amount for all the nodes which would have an other way 0 centrality value. And more importantly, what you can see here, okay, let's read the text. So it's a variation of the cut centrality, in which the centrality derived from my network neighbors and is proportional to their centrality divided by their out degree. Okay, so so now we can take, so to calculate the centrality for node I, we take those xj's which are neighbors. Okay, so these are supposed to be neighbors of node I, and so they are neighbors of node I. Now we take into account their centrality value, okay, and we are normalizing or dividing by the out degree of that neighbor. Okay, so basically this is somehow reduces the simple effect that if I'm just simply connected to a very important node, and that node is important because it's connected to many other nodes, then my connection is not counted fully, because it's the score is divided by that huge number. So that number which corresponds to the degree of that important node. Okay, now it's written here downstairs as a footnote that well, just as a reminder that here, for example, if you want to find out the formula, the meaning of the formula, then you should remember that aij is equal to 1 in case j is connected to I. Okay, so So you see, it's the somehow the transpose of the original adjacency matrix. Okay, so that's the formula for PageRank. Now, if we take the formula and then make it into vector matrix format, then this is what we get, where actually D again, so D is such a matrix. So I should say D inverse is such a matrix that it contains the reciproc values in the main diagonal, the reciproc of the node degrees, okay, and it's a diagonal matrix, okay, and that is corresponding to this division here, okay, and then here the matrix A is represented, okay, X is up there. And then we need the inverse because we are dividing, and beta is beta again. And this both face 1 is the vector which contains ones only. And so with a bit of rearrangement, in a sense that now we should get rid of x here on the right hand side. And with a bit of a calculation, what we get is this formula, which in which we can have two versions, so either this one or that one. And again, you can see here that the formula involves matrix inversion, but in reality, of course, especially for the World Wide Web with billions of nodes, and hence the adjacency matrix is trillions of trillions, trillions times trillions. Of course, we never do the inversion of the matrix. Instead, what we do is again a power iteration. Okay, now so as I mentioned, this was the central part of the search engine of Google, which is really nice that to think about that every time you are looking for a website or a web page which contains your keywords, then it's nice to know that that at the Google servers some eigenvector related problems are being solved on the fly, okay, immediately. And so obviously the real algorithm has lots of details, so it's not this simple formula which Google applies, but in the recent 20 plus years, a large amount of scientists started to work at Google, and then they were keep on improving the formula with lots of additional factors, which we cannot really discuss here because first of all, most of them are hidden or secret things, of course, and the other reason is that it's simply not that interesting from the introduction to network science course point of view. But so one thing which I would like to mention here is that you can see from here that of course Google knows lots of things, so they are really indexing as many websites as they can on a daily basis. But still, of course, there could be many websites which they never discover or they have not discovered yet. And once we are entering queries, then well, it's an experience, of course, which we all know that that most of the times Google returns a useful answer, but it's not because it simply finds the relevant pages, but it does a very good decision what order in what order the results should be presented. So when you enter a query, then of course Google returns with the answer in such a way that the answers are ranked. So what you have on the first page and on the top of the first page are the most relevant hits, findings by Google, suggested by Google. And of course, as I mentioned, they don't know everything, but what they know, they know it, and the task now is to return back a very good ranking. And the success of Google is that one, that they can do very, very good ranking of the web pages. Okay, now the formula contains again an alpha parameter, which we don't really want to discuss, but maybe, why alpha is less than 1 is good. That you can find some details in the book, but maybe still I should mention some kind of interpretation of the formula itself. So actually, maybe not in this format, but on another format which you can find in other places, or maybe even on Wikipedia, the Wikipedia entry on PageRank. But so if you think about it, now maybe I should get back here to this version. So if you think about it, then really the idea was something like this: that let's simulate somebody or a robot who is doing surfing on the World Wide Web. Okay, starting from a certain website, and then randomly choosing another. Randomly choosing from one of the links which are listed on this website on which we are standing at, and then we go to the next website using that link. Then again we click there randomly, and then we go to the third website, and so on and so forth. And so this was actually a random walk procedure, and it is here presented again. Now what makes a difference here is that sometimes also somebody who is browsing the web, he or she gives up, and then gets bored by clicking, and then starts completely randomly on another website which was not connected to the last page, or even to the earlier pages he or she was visiting before. Okay, and so that is somehow related to, in this interpretation, I guess, that is somehow related to this beta factor here. Okay, so that was about PageRank, and now I think this is enough for the fourth lecture. Of course, next week we continue the discussion about centrality measures, and then the next one is going to be hubs and authorities, which I quickly showed you on slide 45. And now I just realized that when I was saying that the PageRank is the last one which we discuss among the eigenvector related centrality measures, then I was wrong basically. So the next one, hubs and authorities, is also related to eigenvectors, but they are somewhat different from what we have seen before, and let me explain that interesting difference only next week. So thank you very much for listening and paying attention. I see you next week.